Okay, let's unpack this. Imagine you're building something really incredible, like a custom designed house. You wouldn't use just one tool for everything, right? Like a hammer for the plumbing. No way. You'd pick, a powerful nail gun for framing, maybe a precision drill for the fine details, a specific laser level, the best tool for each job. That's pretty much the core idea we're diving into today. Polyglot persistence. It sounds a bit academic maybe, but at its heart, it's just about making smart, tailored choices in how your application stores its data.
Exactly. And what's really fascinating is how perfectly this fits with modern microservices architecture. I mean, each microservice is designed to be this independent, specialized worker, right? Responsible for just one specific part of your application. So with polyglot persistence, each of those specialized workers gets to pick the exact data storage solution that's best suited to what it needs to do. It really helps optimize performance, scalability, flexibility. It truly embodies that microservices principle of decentralization. So our mission today really is to give you a shortcut to understanding how all these different databases can actually work together harmoniously, within one application without creating a total mess.
Okay, so if you're thinking, hang on, why manage multiple databases? One seems way simpler.
Yeah.
Well, you've hit the nail on the head. That's the core question. And this is where it gets really interesting because that whole one-size-fits-all database idea, it isn't really cutting it for today's complex, high-demand systems. For instance, different databases are just inherently better at different things.
Absolutely. For optimized performance, polyglot persistence lets services use the best tool for their specific workload. Think about it. You've got your relational database, maybe PostgreSQL. Fantastic for structured data, strong transactional consistency. When you absolutely need reliable atomic operations, can't mess those up. But then you have something like MongoDB, a document database. It's incredibly flexible, great for storing semi-structured stuff like user profiles where fields might change all the time, or Redis, a
Mhm.
key value store. It just shines for lightning fast caching. We're talking millions of reads per second sometimes. A traditional database would likely choke on that.
Right. And that speed thing, it leads straight into scalability. With this approach, each microservice can scale its own database independently. So if your, say, analytics service suddenly gets slammed with read traffic, you scale its database. It doesn't slow down your payment processing database at all. You avoid those bottlenecks you get with one big shared system.
And that separation, it also brings just tremendous flexibility. We're talking about all sorts of different data models here: relational, document, key value, even graph databases. When we say NoSQL, it covers a lot. But think more flexible than traditional relational. Within that, document databases like Mongo store data in these flexible JSON-like documents. Perfect for user profiles, like we said. Key value stores like Redis, super fast for simple lookups, great for caching, session data. And then graph databases like Neo4j, they're specialized for understanding complex connections. Think social networks, recommendation engines, stuff like that. This diversity just makes it so much easier to handle varied data types, different access patterns, and meet evolving requirements down the line.
And crucially, this fits so well with that whole microservices philosophy of decentralized data management. Each service genuinely owns its data and gets to pick its storage, which, dramatically cuts down on coupling across the whole application. It's like giving each team building part of that custom house the best tools for their job, instead of forcing everyone to use the same generic hammer for everything.
Plus, there's a big win for resilience, too. Using multiple databases inherently improves it. If one database, say MongoDB, has a problem, it doesn't take down the entire system. Your user profile service might be temporarily iffy, but your order processing, running on PostgreSQL, it stays completely operational. It isolates the faults, you see.
And the really good news here, especially for developers, is that when you're using a powerful framework like Spring Boot, integrating all these different data stores becomes much more practical. Spring Data provides these fantastic abstractions. Think of them like universal adapters, maybe. They let your application talk to various databases without you needing to learn every single database's unique low-level language. Spring Boot makes it actually doable, not just theoretical.
Yeah, that's a great point, which brings up the question, how do these advantages actually play out in real-world microservices? It really is about tailoring the storage directly to the microservice's specific job, making sure each part of your system can perform at its best.
Okay, let's make this concrete. Let's imagine you're building a big e-commerce platform. How does this polyglot persistence idea actually work in practice there?
Well, for tailored data storage, take a user profile service. It might use MongoDB, right, for its flexible document storage. perfect for user data that can vary a lot. Some users fill out everything, others just the basics. But then your order service, that needs strict transactional consistency. You'd likely use PostgreSQL for that. You need that absolute guarantee. An order either processes completely or it fails completely. No weird half states allowed.
The beauty is Spring Data's repositories, things like JP repository for the relational stuff or Mongo repository for Mongo, they abstract away a lot of that difference. So your code gets a consistent way to interact, even with these very different database types. You're not constantly switching mental gears or syntax.
Exactly. And you see this with independent scaling too. An analytics microservice, maybe it has tons of read traffic but fewer writes. It could use something read optimized like Elasticsearch. Meanwhile, a write-heavy service like inventory management, that might stick with a good old relational database. This lets you scale specific databases up or down based on their actual load without impacting the others or overspending on resources for databases that don't need it.
That makes a ton of sense, and it really reinforces that domain-driven design idea. Like a recommendation service could use a graph database, say Neo4j. Why? Because graph databases absolutely excel at modeling those complex relationships. Users who bought X also liked Y, friends of friends bought Z, it's perfect for that. But a payment service, totally different needs. It would rely on something like MySQL for secure, reliable, standard transactions. Each service picks what serves its domain best.
And this thinking extends to how services communicate, often through event-driven integration. Microservices often chat by publishing and subscribing to events. Polyglot Persistence supports patterns like event sourcing really well, which means instead of just storing the current state, you store every single change as an event, usually in a dedicated event store, like Event Store DB. Then these events can be projected into other databases, maybe read-optimized ones for querying. And tools like Spring Cloud Stream really simplify managing this event flow, keeping your diverse data stores reasonably synchronized. For performance, you can also layer in caching with Redis for super fast reads, or use time series databases like InfluxDB for metrics. Spring Boot integrates these two with Spring Cache and Spring Data Redis.
Right. And the resilience aspect here is huge. Fault isolation. If your MongoDB instance has a wobble, your PostgreSQL database handling orders is totally fine, completely unaffected. And Spring Boot adds layers on top like circuit breakers with Resilience 4j and retry mechanisms to make the whole system even more robust across these different data stores. It's like having separate electrical and plumbing systems in that custom house. One problem doesn't cascade everywhere.
Yeah, exactly. If you connect all these dots, you can really see how polyglot persistence lets each part of a complex system truly thrive. It's using the right tool for its specific job instead of forcing everything into a compromise that might slow down or complicate other parts. It's a really powerful architectural choice when you apply it thoughtfully.
Okay, so if this sounds powerful, maybe even essential for what you're building, how does it actually get built? How do all these different tools come together, especially with a framework like Spring Boot acting as our master builder here?
Well, first, it starts with selection. Each microservice team chooses its database based on its specific needs. So your user service team might say, okay, MongoDB makes sense. Knowing Spring Data MongoDB will ease the integration. The order service team picks PostgreSQL using Spring Data JPA. Maybe there's a cache service using Redis via Spring Data Redis, and an analytics service choosing Elasticsearch, powered by Spring Data Elasticsearch. It's deliberate.
And those Spring Data repositories you mentioned, they're pretty crucial here, aren't they? Providing that unified, consistent API across different database types, it hides so much complexity. Developers don't need to be deep experts in every single database's query language. It's like those universal adapters, again, one way to plug in, connecting to many different outlets.
Precisely. And for keeping things in sync, especially when data is spread out, you often lean on event-driven approaches. Using Spring Cloud Stream with something like Kafka or RabbitMQ, services can publish events, say, an order-created event. Other services listen for these events and update their own local data stores accordingly. It allows different databases to stay eventually consistent across the system. It's mostly asynchronous communication.
And this connects nicely to that pattern, CQRS, right? Command Query Responsibility Segregation. That idea of separating how you update data from how you read it. You can combine CQRS with polyglot persistence by using different databases for read models, maybe Elasticsearch for those fast, complex queries, and separate databases for write models, like PostgreSQL for the secure transactions, optimizing each path.
Absolutely. And of course, with all these moving parts, monitoring becomes incredibly important. You can't fly blind. Tools like Spring Actuator, which gives you production-ready endpoints for monitoring your Spring Boot apps combined with something like Prometheus for collecting metrics, are essential. You use them to constantly monitor the performance and health of all these diverse databases across the system. You need that visibility. So, a concrete example in e-commerce. You might store order events in Event Store DB for auditing, then project them into MongoDB for quick lookups on order status, and cache hot product data in Redis, all managed pretty seamlessly with Spring Boot's different Spring Data modules.
Okay, so what does this all mean for you, the listener? While Polyglot Persistence offers incredible power, it's definitely not a free lunch. There are challenges. It's really important to understand the full picture before diving in. And the biggest one, I think, has to be complexity.
Oh, I agree completely. Managing multiple databases significantly ramps up the operational complexity, no question. It requires expertise in each database type. You need people who really understand MongoDB, PostgreSQL, Redis, whatever you choose. Plus, you need to figure out how to manage synchronization between them, which, like we said, often means dealing with eventual consistency and its implications.
Right, and that leads directly into data consistency itself.
Right.
Often, yeah, you're dealing with eventual consistency. What that means in practice is, after an update happens in one place, there might be a short delay before that change is reflected everywhere else, milliseconds, maybe seconds. You have to design carefully so the user experience isn't confusing or wrong because data is temporarily out of sync. Like maybe an order shows up in my orders instantly, but takes a tiny bit longer to appear in the analytics dashboard. That needs careful thought.
And this also brings up significant operational overhead. It's just more work. Each database type, each instance, needs its own monitoring setup, its own backup strategy, its own scaling plan. That naturally increases infrastructure costs and the sheer effort needed for management compared to just running one big database. It's a definite trade-off.
And you'll definitely find the skill requirements go up. Your development teams need to be comfortable with multiple databases and with Spring Data's various abstractions to build and maintain this stuff effectively. It's not really a beginner-level architecture pattern. Plus, it's crucial to remember, it's not always necessary. Sometimes, maybe often, for simpler microservices with fairly uniform data needs, a single, solid database like PostgreSQL might be perfectly fine and let you avoid all this added complexity.
Absolutely. It's so crucial to weigh these trade-offs carefully for your specific situation. While the benefits, performance, scalability, flexibility can be truly immense, that operational overhead is very real. Understanding when polyglot persistence brings genuine value versus when a simpler approach is actually smarter. That's the key to using it successfully.
So there you have it, our deep dive into polyglot persistence. We've seen how this powerful architectural choice can really empower microservices, letting each service pick the best database for its specific job. And that ultimately enhances performance, scalability, and resilience across your whole application. And, crucially, how frameworks like Spring Boot, especially with its versatile Spring Data modules, make this integration practical and, well, manageable.
Yeah, by aligning with core principles like domain-driven design, facilitating independent scaling, and enabling that tailored data storage, polyglot persistence really addresses many key challenges in building robust, scalable systems today. Especially in these distributed cloud-native environments, it's a fundamental shift away from that old one-size-fits-all database mentality.
So considering both the really significant benefits and those non-trivial complexities we've just discussed, here's something to think about. What if you're building a new microservice right now, or maybe looking at an existing system? How do you really assess if the specialized power of polyglot persistence is genuinely worth the extra operational burden and skill requirements for your specific needs? Or is sticking with a simpler single database solution actually the smarter, more pragmatic choice in that particular scenario?